This video is part 2 of the Fundamental Theorem of Calculus, Unit 6.4. So we have introduced integrals as the area under curves, and now we're going to formalize it in this video. This is the most important concept in calculus because it's called the Fundamental Theorem of Calculus. So let's look at this function g of x from some variable u to a constant a. Now, usually we would use limits and then differentiate. So from the Fundamental Theory of Calculus Part 1, we see that this is going to be f of u minus f of a. And again, capital F represents the antiderivative of f. So it's the integral of f. And we're going to evaluate it from u to a. And this was a corollary of the first fundamental theorem of calculus, which basically said that integrals and the derivatives are inverses of each other. So now if I differentiate this, I'm going to get the derivative of the antiderivative of f. And then times the chain rule. Since we do have u in here, we need to take the derivative of u by the chain rule. And then this is a constant, and so the derivative here is just 0. To clean this up, we know that the derivative of antiderivative is just the function back at u times u prime. And so this is fundamental of theorem of calculus applied to a corollary. So down here, we have the second fundamental theorem of calculus, which basically says if you take an integral from a to b of a function, then it is the antiderivative at a subtract the antiderivative at b. And what that basically says that if I want to find this area under the curve, I would take the antiderivative of f of x, and then I would plug in b first, because it's the rightmost point, and then I would subtract the value at a. And I actually wrote this backwards. Sorry, this is supposed to be b. And so basically, and the reason for it is the antiderivative at b, if I plug in b, it's going to give me the area of all of this to negative infinity all the way to the left. And then I'm just subtracting the area from a, which is here. And then by doing so, I'm left with the area inside. If I do capital F of b, that is the area under the curve from b all the way left to infinity. And then I'm going to subtract it from the area of a, which is the area from a all the way left. And that leaves me with the area from a to b. And there you go. So let's do some problems. And we are going to use this corollary a little bit more in this section. And then when we start moving on, we're going to use this to actually find the integrals from a to b. So what this basically says that if I have an integral, that's going to be capital F, but if I take its derivative, I'm back to my original function. Basically, when I have an integral from a variable to a constant, all I have to do is take u and then plug it in, and then take the derivative of u. Right? So we're going to practice undoing integrals with derivatives, and we will start here. So again, this is the antiderivative because it's capital F. And we are trying to find f prime. So remember, derivatives and antiderivatives undo each other. But when I do the derivative here, I'm not going to just get back cosine. I have to plug in the variable here. And by chain rule, I need to take the derivative of x, which in this case is just 1. So again, if I'm going to take the derivative of the antiderivative, we're going to get our function back, but we do have to plug in 3 the x there. And then by chain rule, we need to take the derivative of 3x, which in this case is just going to be 3. And so I'm going to get 3e to the 6x. Example C, so I'm going to take the derivative of x. By doing so, I'm going to plug in x squared into here. And by the chain rule, I'm going to take the derivative of x squared, which is 2x. So this is going to leave me, after I simplify, with 2x times the log of 3x squared minus 1. Okay, lastly, we see that our variables on the bottom instead of on the top. So we're going to do a little trick. I haven't really showed you, but if you switch your boundaries, so if you go from 2x to 5 and I switch the boundaries, all I have to do is make it negative, and that works. So I can reevaluate this function now. And again, we will show you this rule next section, but little preview. And a way to kind of show this, just to prove it to yourselves, let's say we're going from 0 to b. And let's say we know that the area from A to B is 3 units, and the area from 0 to A is 2 units. And the total area would be 5 units. So if I take the area from 0 to B, that's going to be 5. Subtract, if I take the area from 0 to A, that's 2. So that's going to give me 3. Now if I reverse this, so if I take the area from 0 to A, that's going to give me 2. Subtract. And then if I take the area from 0 to B, that's going to be 5. And notice how I got negative 3. So when you do switch the boundaries, you can just put a negative outside. Okay, finishing this problem, if I want to take the derivative of the antiderivative, I'm going to plug in 2x into here. And then by chain rule, I need to take the derivative of 2x, which is going to be 2. And if I clean this function up, we're going to put the 2 outside. It's going to be 2 square root of 8x minus 1. I forgot to carry down the negative from here to here, so this is negative. And then that means this part is also negative, so there is my final answer. All right, so these are some questions found on the AP exam. Let's just practice them. So I'm not going to show all of these little steps. I will just mention it. But again, we're taking the derivative of an integral. So take x cubed and plug it in. And then by chain rule, we need to take the derivative of x cubed. And in this case, it is 3x squared, which is going to give me an answer of 3x squared times tangent of 2x cubed. Part B, again, taking the derivative of an integral from a function to a constant, plug in the upper boundary to t, and then multiply by the derivative of 2x minus 1, which is just going to be 2. Because if I take a derivative here, that's 2 minus 0. Cleaning this function up, I'm going to get 4 on top, which is the 2 times 2. And then on the bottom, this is going to be minus 12x plus 6 when I distribute the negative 6 through. And so I'm going to get 11 minus 12x. And there you go. There's my derivative of the integral. Part C, same thing. Plug in e to the x there. Times the chain rule. The chain rule, the derivative of e to the x is e to the x. And then if I clean this up, we're going to get e to the x times the square root of 2 e to the x minus 1. Part D, we need to do our trick. We're going to have to reverse these boundaries. So we're going to plug in sine of 2x for t. And then by chain rule, we need to take the derivative of sine of 2x. So the derivative of sine is cosine of 2x. And then we have a second chain rule. And we're going to take the derivative of 2x, which is 2. And so this function is going to be 2 cosine of 2x times e to sine squared of 2x. When I reversed my boundaries, I was supposed to put a negative outside, which carries down to each part of the problem. And so that is my final answer. So we're going to do some multiple choice that was off the AP test. You could see the references there. So in this case, we're going to actually plug in 2. So we're going to take its derivative and then plug in 2. So let's do the derivative first. So if I do the derivative of the integral, I'm going to plug in 2x to t. And then multiply by the chain rule. And the derivative of 2x is 2. So there's my function. Now I just got to plug in 2. I'm not worried about cleaning this up too much. So this is going to be 2 times 2 squared. So that's 16 minus 2 times 2, which is 4. So that's square root of 12. And we still have the 2 outside. So it's 2 times the square root of 12, which is e. 13. Again, we're going to take the derivative of the integral. So we're going to plug in 2x for t, and then by chain rule, take the derivative of 2x. So there's my derivative. I just got to clean everything up. So this is going to be 2x cubed. So we're going to do 2 cubed, which is 8, x cubed, which is x cubed. So this is going to be 2 times the log of 8x cubed plus 1. Okay, we're on our last few problems. Example 3 and another example 3. Need to learn how to count. So example 3 says, let f of x be the integral from 1 to x of that function dt. Find the intervals where you're concave up. So we need to take the second derivative, because concavity is where the second derivative switches from negative to positive or vice versa. So let's interpret the first derivative, or let's interpret the derivative first. So if I'm taking the derivative of these, it's going to cancel. I'm going to plug in x in here. And then I do have to multiply by the chain rule, but the chain rule of x is just 1, so it's the same thing. So let's find the second derivative now. So this is going to be 6x squared. This is going to be minus 6x. And this is going to be minus 12, and then plus 0. So I do need to factor and find my potential points of inflection. So let's set this equal to 0, factor out a 6. It looks like it's going to be x minus 2, x plus 1. So I do need to do the sign analysis. So if I plug in negative 10, I'm going to get a negative times a negative, which is positive. If I plug in 0, I'm going to get negative 2 times 1 times 6, which is going to give me a negative answer. Then if I plug in positive 10, I'm going to get positive times positive times positive. So it looks like we are concave up when the derivative is positive. The second derivative is positive. So it looks like we have negative infinity to negative 1, and then 2 to infinity. So f of x is concave up when we're at from negative infinity to negative 1 and 2 to infinity, because that's where the second derivative is positive. So we're going to do a graphical interpretation of this now. It says the function is defined on the closed interval negative 5 to 4. The graph consists of 3 line segments and is shown in the figure above. And then it says g of x is the integral from x to negative 3 of ft dt. It says find g of 3. So g of 3 is going to be the integral from negative 3 to 3. And again, I am not plugging in 3 into this equation because this is your x value, and your x value only goes here. We don't know. This is just a function that's modeled by this situation. But what we're trying to do is we're trying to find the area under the curve from -3 to 3. So if we come up here to the graph, -3 is here, and +3 is here. So we have this function, or this triangle, that we have to find the area of, and then we also need to find this area. Now, since this is above the curve, or above the x-axis, that's positive, and this is going to be negative area. So let's do the pink triangle first. We're going to get 1/2. The base is going to be from -3 to 2, which is 5. And then the height of the triangle is going to be 4. Then we are going to add the area of this blue triangle. So the base is going to be 1, and the height is going to be -2. And that's where my negative comes from, right? So I could have just done minus here and then just said, oh, this is a 2 height. It's the same thing. But this first area, the pink triangle, is going to be 5 times 4 divided by 2, which is 10. And then subtract. The area of the blue triangle is 1. So that means my total integral is 9 units. Part B, what open intervals contained from -5 to 4 is the graph of g both increasing and concave down? Give a reason for your answer. So if you recall, g of x is increasing when your derivative is positive. And g is concave down when the derivative is increasing. So we need to find out. Oh, I'm sorry, I misspoke. It's decreasing, not increasing. So g is concave down when the derivative is decreasing. So we need to find out where the derivative is both positive and decreasing. So how are we supposed to do this? Well, let's take the derivative of g and see what we get. So g prime of x. Now, since it's the derivative of the integral, all I have to do is plug in x. Oh, so my derivative is just my original function. So where is the original function? Positive. So let me make a note here. Because again, we want to know where the derivative is positive, but the derivative is just the original function. So where is the function positive and decreasing? So it looks like we're positive and decreasing in that interval and in this interval. So we would say that this is from -5 to -3 and from 0 to 2. Last one, it says the function is given by h of x equals g of x divided by 5x. Find h prime of 3. So this is going to be a product rule. I mean, a quotient rule, sorry. So if I take the derivative, I'm going to get we have two functions that are divided. So it's going to be the derivative of the top times the bottom. Subtract the derivative of the bottom, which is just 5, times the top, all divided by 5x squared, or the bottom squared. So let's plug in 3. This is going to give me, again, if I plug in 3 here, I'm going to get 15 times the derivative at 3 minus 5 times the function at 3, all divided by the bottom. If I plug in 3 here, I'm going to get 15. 3 times 5 is 15 squared, which is 225. And so now we just need to find what the derivative is at 3 and what the function is at 3. Now, if you look at part A, we already figured out what the g of 3 is. So this is going to be 9. And we know that the derivative at 3 is just going to be the function at 3, because we did in part B, we did the derivative. So the function at 3 looks like it's going to be negative 2. So this is going to be 15 times negative 2, which is negative 30, minus 5 times 9, which is 45, all over 225. So that's going to be negative 75 over 225. And then if you divide the top and bottom by 75, you can get negative 1/3.